Hey guys, so I promised I would record the video of me going over the review, and so here you are. So this is for your test tomorrow on stoichiometry, and so let's spend a few minutes talking about the important things going on in this test review and go through some practice problems. So just to recap, there are a couple of like main things that we learned about that are covered on this exam. So the first thing is just kind of like introducing stoichiometry and what it is. Okay, so we're going to talk about that a little bit, why we would use it, and then we started to use it to convert mole to mole and gram to gram. And then finally, we spent some time learning how to calculate our percent yield. All right, so that's when we are comparing what we got in the laboratory in terms of like how much product we yielded from the reaction compared to how much we could have. And we found out how much we could have because of all this stoichiometry that we learned. So, so let's just take a minute to look at these terms. Okay, so mole ratio. I just want to start by saying that when it comes to definitions, that's kind of low-hanging fruit on a test, right? I mean, it's that's just studying, okay? And so this test is kind of heavy on calculations, of course, but you want to make sure that you take a few minutes to get the easy stuff down, all right? Because those are points that are just on the table, ready for you to take with little effort, okay? So let's talk about mole ratio. So, the one thing that I want you to remember when you're thinking about mole ratio is the word relationship. Okay, relationship. All right. It's the relationship between substances in a chemical reaction. All right. So, relationship between substances in a chemical reaction. Okay, relationship between substances and a chemical reaction. And we use these relationships to convert from moles of one substance to moles of another substance. Okay, so that's where our mole ratio comes in. So again, you want to focus on the word relationship because that's what it is. That's what a ratio is in general. All right, let's talk about this next word, limiting reactant. And let's talk about excess reactant. Okay, so just thinking about our equation, we know that A plus B that yields C plus D, that A plus B here, these are our reactants. Okay, and so just like when you go to your cupboard, you have ingredients, right, that you might use to make a recipe. All right, these are our ingredients, A and B. And some of those ingredients are going to be in excess, meaning that, even after we make our recipe, we're going to have some leftover. So the key word that you want to think about when you're thinking about excess reactant is leftover. You're going to have leftover, okay? And then, but one of the ingredients in a chemical reaction is going to be the one that is the deal breaker for making any more because it's simply all used up. Okay, so all used up or used up, let's just say, is I think what we want to remember for limiting. Okay, the limiting reactant is used up in the reaction. Just like if you were to go and take out some like 3 pieces of meat from your refrigerator and you have 50 pieces of bread, it will not matter that you have 50 pieces of bread because you can only make 3 sandwiches, assuming you're going to use 1 piece of meat per sandwich. Okay, so in this particular example, the meat would be limiting. All right. So just remember that you want to remember that limiting reactant is the one that gets used up in the reaction, and that the excess are ones that are left over. Sometimes you might just have one excess reactant. Sometimes you might have multiple excess reactants. But those are the things that you need to remember. All right, so let's switch gears a little. We have more definitions, but now we're jumping to the concept of percent yield. So let's talk about percent yield and what it even means. All right, so percent yield, okay, it equals, the formula is actual over theoretical, all right, in parentheses, times 100. And again, we kind of likened this to calculating your grades. Okay. So yield, as we learned in the last unit, basically kind of means just to produce, right? So up here, this arrow, this is the yield sign, right here. And so I'm pointing to it with my arrow just to show you that, these two chemicals react and then they yield other chemicals. So the percent yield simply means that there's some amount of chemical that you should have been able to acquire in your chemical reaction, maybe that you were doing experimentally. And so it's not necessarily the amount that you actually do um, recover in your process. And we learned that in lab because our percent yields were all over the place. Some of us got over 100%. We talked about how that could have happened. Some of us got under 100%. We talked about how that could have happened. In the real world, you're more likely to get under 100%, right? Because is it really possible with the law of conservation of mass where we can have more atoms of something than we started with? It is not. Okay, we learned last unit that we have to end with whatever we start with. All right, so that's just kind of like a refresher on why we would want to do percent yield and what the formula is. So actual yield, there are some key words, okay, that I want you to think about when you're trying to figure out, all right, which of these numbers goes on top and which on bottom when we're doing our calculations. So some of the key words that you want to think about is like if you see the word like the scientist or the student, okay, that means it is something that you did or a person did in a lab, okay? Scientist, student, measured something, okay, measured their product or something like that. It's data that they collected in the lab, okay? We'll just say product in lab. Maybe it's a classroom lab, maybe it's a real lab, okay? So the scientist or the student, the person, all right? So that's the information that's going to go on top. So let's think about that in something that like you use every day. You guys calculate, we get grades every day where someone has calculated this for you, all right? So the actual, when you're talking about your actual grade, let's do this one. So let's say I've given you back your quiz and you got 20 out of 21 points, all right? So the way that your final grade is calculated is you take your top number, which is the actual amount that you earned, over what's possible, okay? Percent yield is no different, all right? So your actual amount is what you did. And then underneath the theoretical amount is kind of like what is possible. So what is possible is what we calculate with stoichiometry. So let's see here. Some words that you might see in your problem that would indicate that we're talking about the theoretical number. Okay, so some of the things you might see are like the maximum amount, maximum amount. All right, so think about how that relates down here. If 21 points is all that's possible, that has to be the maximum amount. Okay. So every single time we're doing that gram to gram calculation, we are trying to figure out what is the maximum I could possibly get out of this reaction. And then the actual is how much we are actually getting out. And so the result is some percentage of what we could have gotten, just like your grade is some percentage of what you could have gotten. Okay, so maximum, that might be something that you would see. I'm going to think about some more of these. All right, so another one that you would see is like calculated, the word calculated. Why would we see the word calculated when we're talking about theoretical yield? Well, that's because it's mathematically proven, okay, that, and honestly, the whole body of knowledge from science says that these numbers on the periodic table are true and that we can relate mass to moles using the periodic table. And so and in theory, okay, that's kind of that theoretical word. In theory, we should be able to use all of the information from the scientists that came before us that developed all of that great information on the periodic table to get our theoretical yield. So it's calculated. That's another one that you might see a lot. All right. So these are just some words that you might see, but basically it is like it is the yield That's possible. Not necessarily what you got. Okay, let's move on. So what do the coefficients in a chemical equation represent? All right, so let's look at this one below. This is a s'mores equation, so it's not a real chemical equation, but we have some coefficients. So just a reminder, these are our coefficients here, 2, 1, 4, 1. We learned all about coefficients when we were balancing equations. So, all right, it says what do the coefficients in the chemical equation represent? So in this particular case, these are relationships, okay? They're moles, okay? So 2 moles, I mean, assuming that we were talking about moles, right? 2 moles of graham crackers plus 1 mole of marshmallows plus 4 moles of chocolate pieces will equal a s'more, okay? We really don't want a mole of any of those things. That would be a ridiculous amount of space that would take up. Um, so, but it's basically representing the mole relationship, okay? Dalton's postulates, he said that atoms combine in whole number ratios. It was pretty amazing that he knew that way back then, but it is true and it is the basis of so much of what we do in chemistry. So what do the coefficients in a chemical reaction represent? They represent the number of moles of the substance or chemical. Oops, let's fix that up. Of the substance. All right, now it says, given the recipe for s'mores to the right, or underneath here, calculate the following. It says, if I have 26 graham crackers, how many chocolate pieces will I need? All right, time out. Let's just talk about like anytime we're doing one of these where we have to, calculate something or analyze our problem or do something like this. Just remember, you only have a couple of different methods that I've taught you to do these conversions and use these mole ratios. All right. So in this particular case, the first step, no matter what type of problem it is that you got to write down the number that's given. So in this case, we have 26 graham crackers, which we are going to label as GC. Okay, 26 graham crackers. So now, just like in a chemical equation, we need to understand the relationship between graham crackers and chocolate pieces because graham crackers is what we were given, all right? And chocolate pieces is what we're trying to find, okay? So just keep in mind that the relationship, this mole ratio, is always going to be what you want. Oops. Let's make that prettier. Okay, it's want over given. Okay, that is the mole ratio. And so we're going to use that in every single mole to mole conversion or anytime you have a balanced equation and they're asking you to find the relationship and apply it. Okay, so we also learned that in dimensional analysis, okay, which is the way that we can take something and accurately represent it in a different unit using these relationships like mole ratio. So the unit right here is graham crackers. All right, so graham crackers has to go here. And then our, let's see, we want chocolate pieces, and we know that mole ratio equals want over given. Okay, and so if chocolate pieces is what we're trying to get to, we're going to leave it up here. So now we just have to use our balanced equation to find out what we need to put for each. So we have 4 chocolate pieces according to our balanced equation, and we have 2 graham crackers. So for every 2 graham crackers, we need 4 chocolate pieces to make a s'more. That's basically what it's saying. And so the math in our calculator ends up something like this. Okay, there are a million ways to actually do this calculation. So you are multiplying everything across the top, and I multiply everything across the bottom and then just divide those 2 numbers together. All right, and so when I do that, I take my calculator. I mean, I could make this problem simpler, okay, by doing it like this. There are so many ways that we could do this. And you would just get 52 chocolate pieces. So whatever is the unit that is up here is the unit that your answer will be in because you are crossing out your units. You're canceling them out, just like in any kind of math problem. We're going to cancel those out. All right, the next one says, how many s'mores can be made from 28 graham crackers, 22 marshmallows, and 44 chocolate pieces? All right, so we talked about in class that when your problem has multiple numbers given, okay, you have to set up a separate problem for each one. So just for the sake of time, I'm going to do that here, and I'm going to do them kind of all at the same time. Let me do this a little differently. All right, so let's just write down our numbers. That's always step one. So I have 28 graham crackers, I have 22 marshmallows, and I've got 44 chocolate pieces. Okay. All right, so now I just have to put my relationships in here. All right, my mole ratios. Of course, these aren't real moles, but it's conceptually the same thing. So we're trying to get to s'mores. S'mores is what we need to end up in. Okay, so it's the s'more relationship. Oops, that's pencil. It's the s'more relationship that we care about. So for all of these, we're going to have one s'more that we're trying to make. And on the bottom, we have to match the units so that they will cancel. So marshmallows have to cancel, chocolate pieces have to cancel. And so now we're going to go to our balanced equation up here at the top, and we're going to define these mole ratios so that we can use them. So we know that how many graham crackers do we need for one s'more? Well, it says 2. So I'm going to put 2. How many marshmallows do I need for one s'more? Well, our balanced equation tells us we just need 1. And then the next one says how many chocolate pieces, or I'm sorry, yeah, how many chocolate pieces for one s'more? We have to define this relationship first. And so it says 4 chocolate pieces. Okay, so let's do the math here and make our lives easier so that we can tell which one of these is the real answer. All right, so for this one, we're just going to say like 28 times 1 divided by 2. All right, so that's going to get us 14 s'mores is that answer. And then this one is just 22 because these ones will cancel out. So 22 s'mores. And then this one over here is 4 divided by 44, okay, which is 11 because, again, we're going to multiply across the top and then divide the bottom. So if you take 4 out of 44, you just have 11. And so now we have 11 s'mores, okay. So we have, let's do SM for s'more. Okay, so we have 11 s'mores here, 22 s'mores here, and 14 s'mores here. But not all of these are the actual answer. Only one can really be the answer. Because if these ingredients are what you have in your cupboard, you will never be able to make more than your limiting ingredient will allow you to make. So, I use this example in class all the time. If you have 100 pieces of bread and you only have 3 pieces of meat, you can only make 3 sandwiches, assuming that you have 1 piece of meat per sandwich. So on this particular problem, you really can only make the lowest number possible. All right, which and that's how it's going to be for all of these problems, whether we're doing moles to moles, grams to grams, anything that we're doing. You're always going to pick the lowest amount, and that is going to be the final answer for that problem. And then you're almost always going to see some kind of question where it asks you like, what is the limiting reactant? So let's remember that in a chemical equation, our reactants are over here on the left. Okay, so these are the reactants. And so when it asks you for the limiting reactant, you want to make sure that you're choosing what's on the left side of the equation, right? So reactants here are graham crackers, marshmallows, and chocolate pieces. So if the chocolate piece, the marshmallow, and the graham crackers are reactants, then the one that made the least amount or yielded the smallest amount is going to be the limiting one. So in this case, it's going to be that the chocolate pieces are the limiting reactant. And then it says how much of the excess reactants are left over from part B. So I'll be real honest. We did not talk in class about like I never had you actually calculate how much was left over. The real value in this question for you guys is understanding that excess reactants are left over, like that they will have leftovers. Okay, but let's just go ahead and conceptually like just walk through this. So if you have 11 s'mores, that's as much as you can make. Imagine you're at your kitchen and you brought on the counter 28 graham crackers, 22 marshmallows, and 44 chocolate pieces, and you've assembled 11 s'mores. You're going to have enough ingredients, okay, to have 3 more s'mores for, like if you were just based on the graham crackers. And to get to 3 s'mores, because you need 2 graham crackers per every s'more, it's actually going to result in 6 graham crackers. So graham crackers is an excess reactant, and you have 6 left over after we do all this s'more making. Okay, and then finally over here, we have our marshmallows. All right, so if you take the amount of marshmallows that we need, okay, you really just need 1 marshmallow per s'more, and we have made 11 s'mores. Okay, so that ends up with 11 marshmallows left. Okay, so we have 11 marshmallows left after that. So the marshmallow is an excess ingredient, and we have 11 left. That one, I will say that one was kind of confusing just because we hadn't talked about it exactly in those words. But the important thing to think about for your exam is that the excess reactants are left over. You'll have leftovers. Okay, so here we go. Now we're kind of getting into the meat of things. Okay, answer the following questions given the reaction. So just like this, your exam will have, various balanced equations, and you'll have to answer several questions that are based on that equation. So it says, what is the mole ratio of diatomic chlorine and iron? All right, so we just have to make sure that when we're writing out the mole ratio, that we're actually using the appropriate order of things. Okay, that's the biggest thing that I saw in the quiz. So with diatomic chlorine, okay, there are 3 moles. All right, that's the first one that it talked about, and so that's the first one we want to write. And then iron has 2 moles, and so that's the second one we want to write. Okay, so just remember to get it in the same order as it is given to you in the question. That's the big takeaway. All right, it says calculate the number of moles of iron needed to react with 5.87 moles of diatomic chlorine. All right, so the first thing we do in every problem, no matter if it's an easier mole to mole conversion or one of the more complicated gram to gram conversions, you want to go ahead and start with writing your problem down. That's always the first step. Okay, so 5.87 moles is what we're given. But not just moles, moles of diatomic chlorine. That's important because if you aren't sure what unit you're in, and by unit I mean moles of diatomic chlorine, if you're not sure, then you won't know what to write next. But if you do know and you remember that whatever you wrote down for that unit has to be the unit that you write down on the bottom of the next step, then half your problem is already done for you. Diatomic chlorine, it's the same, okay? And what we're looking for goes on the top. So remember, mole ratio is always what we're given over what we want to find. Okay, what we want to find, our unknown. So in this case, it is mole of iron is what it says from our problem, because this is what we were given and this is what we need. All right, so now what we need to do is just plug in our mole ratio, the relationship. That's how we're going to do the conversion. In the same way that we would convert, maybe seconds to years using relationships in time, like 60 seconds in a minute, 60 minutes in an hour, that kind of thing, until finally we get to the unit that we're looking for. So here we have moles of iron, and so this is up here in our balanced equation. We can see we have 2 moles of iron in this equation, and we have calcium chloride. We have 3 for calcium chloride. Okay, so now we just need to do the math here. So we're going to do oops, that is not pretty. 5.87 times 2 over 3. And so let's do our math. So just to be clear in the calculator, because I know sometimes that is a struggle, I just do 5.87 times 2, all right, and then whatever that is, I just hit that division sign, okay, and divide by whatever is on the bottom. In this case, I got 3.91, and the unit is moles of iron. Okay, that's what we needed, and that's what we were left with here, so we're good. 3.91 moles of iron. Then it says, how many moles of iron chloride can be produced from 4.7 moles of iron? So again, first step, write down your given. 4.7 moles of iron. Now we got to go find that relationship. The relationship is moles of iron are here, and moles of what we're looking for are here. Okay, so we go to our balanced equation and we see that there are 2 moles of iron for every 2 moles of iron chloride. Well, that makes a really easy math problem for us because these cancel out and we're just going to have 4.7 moles of iron chloride. Perfect. Let's box our answers for clarity. There we go. All right, now we have another one where it says how many moles of iron chloride can be made given 8.05 moles of iron and 6.55 moles of diatomic chlorine. Okay, so I'm given 2 numbers here, so that should immediately tell you that I have 2 different things to set up. Not only do I have 2 things to set up, but I'm anticipating that they're going to ask me about which one's limiting, which one is an excess, and so I can kind of start thinking about that. So let's just set that up. Again, the first step's always to be writing what you're given. 8.05 moles of iron, and then we have 6.55 moles of diatomic chlorine. Okay, writing my train tracks for my dimensional analysis here. So we talked about this. We have to write the same units diagonally. So we have moles of iron and moles of diatomic chlorine. Okay, and so what we're trying to find is the moles of iron chloride. So let's do moles of iron chloride. And same thing over here. One of these answers will be the real one. Let's see which one it is. So let's define our relationship here using our balanced equation. So iron chloride, we have 2 moles. And for iron, we have 2 moles. Love that. That's an easy math problem for us. Okay, and then so now we have diatomic chlorine, which has 3 moles. And then, of course, iron chloride, 2 moles. So for this one, these 2's are just going to cancel. And so we're left with 8.05 moles of iron chloride. Why? Because not only did those 2's cancel, but these units canceled, leaving us with moles of iron chloride. All right, so that is one possible answer for this. Let's look at this one. So this one's math is just ever so slightly more challenging, right? So 6.55 times 2 divided by 3. And let's just see what we get in here. 6.55 times 2 divided by 3. And that is going to be 4.37, let's say. 4.37. We are not worried about significant figures in our class at this time. So if you end up rounding a little bit differently, it's okay. Just choose the answer that is closest to the answer that you got. Okay, so 4.37 moles of iron chloride. Okay, so you have 2 answers for this problem, but are they both possible? No, because you can never make more sandwiches than you have meat to make, okay? Thinking back in our sandwich and meat situation, all right? You'll never be able to make more sandwiches. So if you have, it doesn't matter if you have 100 pieces of bread if you only have 3 pieces of meat. So one of these is like the 3 pieces of meat, and one of these is like the bread, all right? And so you know which one is the meat because it's the one that produced the least. This is the limiting reactant here. Limiting. Okay, so this itself is the right answer, and this is the limiting reactant because we talked about up here that the reactant are one of these things on the left side, and these other things are the products. So your answer has to be a reactant from the equation, not the product. So on the quiz, I saw a lot of product answers and I gave some partial credit because I knew what you meant. You meant, hey, it's this one. This is the right one, the one that produces the least. Okay, so we're moving right along. All right, these questions still apply to that same balanced equation from before. It says using the answer from part D, which reactant is limiting and which is the excess. So we already kind of talked about that. So the limiting is going to be our diatomic chlorine. All right, so limiting, let's say, limiting is our diatomic chlorine, and that's because we it produced the least. All right, produced the least product. Okay, and then the excess, that's going to be our iron, because after we use up all the iron making our iron chloride over here, we will have run out of diatomic chlorine and we won't be able to make any more iron chloride, but we'll still have some iron left because this is the ingredient like the 100 pieces of bread. All right, so our excess is going to be the iron. Okay, we have stuff left over. All right, so if 6.0 moles of iron makes 6.0 moles of iron chloride, and 6.0 moles of diatomic chlorine makes 4 moles of iron chloride, which of these is going to be limiting, iron or diatomic chlorine? So let's look at this like this. When you see things like this and you're not sure what to do, start unpacking it. Okay, what I mean by that is start writing things down in a way that is more clear. So I'm going to just write down what's in this problem, okay, in a way that kind of makes more sense to me. All right, so let's see. The first thing it says is 6.5 moles of iron is it makes, so I'm going to do the yield sign. It makes 6.0 moles of iron chloride. Okay, so that's the first piece of information it gave us. And then it says also 6.5 moles of diatomic chlorine yields, it says makes, but that means the same thing, 4 moles of iron chloride. Okay, think about it like this. This is like saying 6 pieces of bread makes 3 sandwiches, and 6 pieces of meat makes 4. Okay, or whatever, something like that. It's basically saying these are the ingredients you have. One of them makes this amount here, and one of them makes this amount. Which one is limiting? Well, just like in the problems we just looked at, it's going to be whichever produces the least. Okay, the least amount of stuff. So if iron chloride, if this reactant here, our diatomic chlorine, is the one that's producing the least amount, we don't really have to do any calculations. Okay, if you see like a ton of numbers there and it says something like this is, this is how much we have and this is what it makes, it's really a simple problem. And sometimes it's hard to find a simple problem, or it's easy to be tricked by a simple problem because you kind of go into it thinking, man, I gotta like bring every, technique, every bit of knowledge about molar mass or mole to mole, all these things that we've learned. But really, when you break it down and write it in its simplest form, you see that all it is the problem that we just did. But the math is kind of already done. It's basically these problems but just done for you. Okay. All right, so we're getting through it here. Okay, so now we have a balanced equation, and already in the corner of my eye, I see that dreaded word, grams. Okay, so this is our gram to gram conversion. It's the hard one, right? Is it hard? Well, it takes practice. I think that that's the takeaway. So it says calculate the mass in grams of magnesium needed to react completely with 14.5 grams of diatomic oxygen. So I know already some of you are thinking, oh, wait, react completely. Should I know what that means? Should I be doing something differently because it says react completely? The answer is no. Okay. This is the same thing that we've been doing. All you have to do is write down your given number. That's always your first step. It doesn't matter if we're doing the longer conversion where we go grams to grams, or if you're doing a shorter mole to mole conversion, your first step's always just to write down what you're given over here. Okay, so it says calculate the mass needed of magnesium needed to completely react with 15.4 diatomic oxygen. So 15.4 grams of diatomic oxygen. That's what we're starting with. And I already know because I have grams in my problem that I'm going to need to use my molar mass of not only what I'm starting with, but also what I need to end up in. Okay, so my starting unit is O2. Okay, I just know because there's no way I'll ever be able to forget that oxygen is 16.0. Okay, so that makes O2 32. So my molar mass is 32 grams per mole for O2. And so our 32 grams, we're going to go down here because we always have to match the units, just like we just did in the other problems. So those cancel out. And if you'll pay attention to our unit for molar mass, we see it's 32 grams per mole. That's the same thing as saying 32 grams per 1 mole of O2. It's just the same thing, okay? So now we're going to do our next step, which is our mole ratio, because we see here that this is moles of O2, and so moles of O2 have to go here. And we know because this is the mole ratio step, it's where we make that leap from what we're given to what we need. All right, so we're going to match it up here, and so we have to talk about relationship now. Okay, so moles of O2 is what we were given, and we need, from our problem, it says we need magnesium. So that means moles of magnesium have to go here in our molar mass step. Okay, so moles of O2, we just have 1. And moles of magnesium, we have 2. And so we're done with that step. Okay, our final step is now we need to look at the molar mass of magnesium, I guess, oxide. Okay, so let's go, or actually it's just magnesium. It's just magnesium. All right, I'm actually going to need to look up the molar mass of magnesium because I did not bring my periodic table home. All right, periodic table, let's just say moles of magnesium. Or no, molar mass. Molar mass of magnesium. Our molar mass, I mean, 24.31, let's say. Okay, so 24.31 grams per 1, or nope, sorry, that is wrong. It is 24.31. But it goes up here, 24.31 grams. How do I know it goes up here? Well, because these units have to match, right? So 1 mole of magnesium, because the unit for molar mass is grams per mole, has to go on the bottom because we know that these always have to match. Our units have to match diagonally, okay? That will always help you know you're on the right track, and it will save you from making a mistake. But the problem is it takes effort to write out the grams and the unit on every single step. But what happens is once you get several steps in, if you are not identifying your moles of what chemical, are you dealing with chemical A, you're dealing with chemical B, are you dealing with moles, you're dealing with grams? If it's not super clear to you, then you're going to make mistakes. Okay, I guarantee it. All right, let's talk a little bit about how I'm going to put this thing in my calculator. All right, so I just find that this has the least mistakes in these TI-84 calculators. So 15.4 times 2 times 24.31. Okay, so I did not include this 1 here, over here. Oops, that's probably best for a highlighter. Okay, yes, here we go. Yeah, so like, you see this number 1 over here. I did not include that over here because it's 1. So like, we don't need to times anything by 1 necessarily, but if you did, it's fine, okay? And so we have that on the top. So you're gonna put that, each of those things in your calculator and hit enter. Then you're gonna hit that divided by symbol. And then on the bottom, we're more or less doing this, 32 times 1 times 1, which I'm not actually going to put those ones in my calculator because it's kind of a waste of time. But if you did it, it's not going to hurt anything. The point is you need to multiply all the things in the top. You're going to have some number that you get, okay? And then you're going to hit divided by, and then if there's multiple numbers that you need to divide by, you want to put these in parentheses. So I say 32 times 1 times 1 if I was putting all of that in my calculator. And my result is 23.39. All right, it's actually we're going to round to 23.4. 23.4 grams of magnesium. Okay, that is the final answer. All right, so next it says calculate the mass in grams of magnesium oxide that can be formed from 12 grams of diatomic oxygen. Again, we are just going to write out what we are given and go from there. Okay, I'm going to do this one a little bit faster so that you can just kind of see the value in matching the units and how it can speed up things for you. Okay, so it's just kind of a pattern recognition thing, a little time saver that I do when I'm doing these problems. Okay, I just start copying the units down because it makes it so much faster for me. So I know this is my mole ratio step, and so now I need to make that leap from that diatomic oxygen to magnesium oxide. All right, so now I've got that there, and now I'm going to copy that unit. Okay, magnesium oxide. And on the top, I need my molar mass, which is going to be in grams of magnesium oxide. So I need to go, first of all, let's just highlight the fact that this unit matches this one, and that this one matches this one, and that this one matches this one. Okay, that has to be the case because in dimensional analysis, the way that we're getting to our new unit from the unit we started with is because we're able to cancel the units out. Okay, but now we have to go in and plug in our numbers because there are a whole bunch of places that where I haven't put anything in. So we need to have diatomic oxygen. We calculated the molar mass of diatomic oxygen earlier. It is 32.0, 16 times 2, because we have 2 atoms of oxygen. And now we need to find our mole ratio from our balanced equation. All right, that is the stoichiometry part. We've got to use that relationship to figure out how much we can make based on how much we're given. So our moles of O2 are just 1 because there is the implied coefficient of 1 in this balanced equation. And so on the top, we have moles of our magnesium oxide, which is right here, and that is 2. All right. Okay, so let's see here. We need to calculate the molar mass for magnesium oxide for this step because we know that we have 1 oxygen atom, which is going to be 16. Okay, so 16 is the molar mass for 1 oxygen atom. And then the molar mass we calculated, or we looked up earlier on Google or whatever it was, that the molar mass of magnesium was 24.31. Okay, that's magnesium. So when we're calculating molar mass, we just have to account for the number of atoms of each type of element that are in a compound or molecule or whatever it is, and we just add them together. Okay, so let's say this is going to be what we have: 1, 3, 4, 40.3. Is that right? Let's see here. I think that's right. Okay, so like 40.31 grams of magnesium oxide. All right, in our calculator, this is what we're going to do. 12 times 1 times 2 times 40.31. Okay, that's the top of the dimensional analysis train track situation. And then underneath, okay, so in my calculator, I'm just going to put all of those numbers, and then I'm going to hit enter, and then I hit the divide button, and in parentheses, I do 32 times 1 times 1. All right, so let me do that and see what we get. 12 times 1, which I don't really need to do, times 2 times 40.31. And then I hit enter, divide, and in parentheses 32 times 1 times 1. It's 30.23. All right, let's say 30.23 grams of magnesium oxide. That is our answer. All right, now we have one that says, how many grams of magnesium oxide can be made given 125 grams of magnesium and 72 grams of O2, diatomic oxygen? Okay, so just like in the mole to mole conversion, we have to do these problems separately because only one of these are real. It's like saying, like, you have to figure out how much you can actually make, because you only have certain number of ingredients in your cabinet. Okay. Okay. So let's see here. The first step always, and I'm going to set these up kind of at the same time. I have 125 grams of magnesium. I have 72 grams of diatomic oxygen. All right. Getting myself all set up here. I know that step one in this problem is to write my given. Right? Given. That is not even legible. Here we go. Okay. You're going to write the number you're given. How about that? Number two is molar mass of given. Okay. And it's going to be moles, 1 mole, over the molar mass in grams. Step 3 in the problem is your mole ratio. And step 4 in your problem is going to go back to molar mass, but now you're dealing with what you want. So molar mass of what you want to find out. Okay, and that is going to flip where grams will be on top and 1 mole will be on the bottom. Okay, so this is the general framework that we have talked about. So according to this framework, step 2 is molar mass of given, okay, which is going to be 1 mole over whatever the molar mass is. So the molar mass of magnesium we already found earlier was 24.31 grams of magnesium. Our units match. We're good. Okay, over 1 mole of magnesium. We got to put our same unit down here, mole of magnesium. All right, and what are we trying to find? Well, we're trying to find moles of magnesium oxide. So let's find our mole ratio. Our mole ratio says that we have 2 moles of magnesium oxide for every 2 moles of magnesium. Gotta love that. They cancel each other out. Great. All right, so now we need to put moles of magnesium oxide down here because we have to be matching these units diagonally. All right, and so grams is going to end up here because we said step 4, molar mass of what we want. Well, what we want is magnesium oxide. So the molar mass, I think we said was 40.31. Okay, 40.31 is what this should be. And that's just going to be 1 mole because the unit for molar mass is grams per 1 mole. And so we're going to do the math in a second, okay, on that. So let's come over here and just get this one all set up as well. Okay. Okay. So this one, like, let's match our units, grams of O2. We already calculated that the molar mass of diatomic oxygen is 32 grams per mole. So 1 mole of O2. And now let's copy our unit diagonally, 1 mole of O2 or some moles of O2 to what we want, which is going to be moles of magnesium oxide. And if we go up to our balance equation, we see we just need 1 and then we need 2 magnesium oxide. Let's copy our unit, moles of magnesium oxide over, or it's just going to be grams because step 4 is our molar mass of what we want, grams over mole. So grams of magnesium oxide is here. And so let's see. This is always going to be 1 because the unit for molar mass is grams per mole. And magnesium oxide, how many grams of magnesium oxide? Well, what did we say it was? It was 40.31. Oops, 40.31. All right. So we're going to multiply all the numbers across the top. I'm going to start with the first problem. 125 times 2 times 40.31, and then I hit enter. And I'm going to divide by 24.31. And again, I put this in parentheses, times 2 times 1 in parentheses, and I got 207.28. 207.28, okay, grams of magnesium oxide. So that is one possible answer to this problem. Let's do this one. All right, it says 72 times 2 times 40.31, enter. divided by, and we only have one real number on the bottom. I mean, because 32 times 1 is 32. So I'm just going to divide by 32. And for this one, I got 181.3. Actually, it's going to round to 0.40. So 0.40 grams of magnesium oxide. All right. So these are the two possibilities, but there's only one real answer. It's got to be the one that makes the least amount. So this is our only real answer to this question. And then it says, using the answer from part C, which reactant is limiting? Well, we already discussed that the reactants are on the left side of the equation. Okay, so magnesium and diatomic oxygen, these are our reactants, and that our limiting reactant is going to be the one that produces the least. So in this particular case, our limiting has to be our oxygen, our O2, okay? And that means the excess is the other one, all right? The one that produced more, which is magnesium, okay? There you go. All right, and then finally, this is kind of a similar question to what we had before, where we were given the information and the math is done for us already. So it says 50 grams of magnesium are going to yield 2.1 grams of magnesium oxide. Great. Let's just highlight that. Okay, so magnesium is producing 2.1 grams of magnesium oxide. And then it says 50 grams of diatomic oxygen is going to yield or produce 3.1 grams of magnesium oxide. Okay, so one of them, the point is, one of them produces 2.1, and then the other produces 3.1. Which one is limiting? Well, we already know that the limiting one is going to be the one that produces the least amount. So let's see here, magnesium, so let's just say magnesium produces 2.1, and diatomic oxygen is producing 3.1, and so this one has to be limiting, the magnesium. All right, that's pretty straightforward, I think. All right, now these next questions are even more straightforward. More words, okay, and numbers, but less work. All right, because these are our percent yields. These are the questions about percent yield. So let's think back when we started this review video about some of the keywords and things that we were thinking about, okay, when we want to know like which one is going to be the actual yield, which one is theoretical yield. So it says that we might need to be looking out for words like, for actual yield, like the scientist, the student measured, something in a laboratory experiment, that's going to be actual. And that theoretical might say something like the maximum value of, or, what you calculated or what you should have gotten. Okay, that's something I didn't even write down over here, but that's another one that you will see is should have gotten. Like the student should have gotten this much product. So should have gotten is definitely a clue that you're talking about theoretical. So let's apply that. So it says, before you and your lab partner started your lab experiment, you calculate the theoretical yield of magnesium oxide to be 36.77 grams. All right, 36.77 grams. So let's highlight some things in here. You calculate, and this one even says theoretical, okay? To be 36.77 grams. So let's remind ourselves of the formula. Percent yield equals actual over theoretical, okay, in parentheses, times 100. Okay, so this one's pretty clear. It even says theoretical. This is what it is. All right, so that means that the theoretical, the 36.77 is on the bottom. And then it says, once the experiment was complete, you only measured. So you measured, just like I was saying, the chemist, the scientist, the student, that's the you in this question. You're the student. And you measured 28.95, okay, grams. And that's the same thing as saying you earned a certain number of points over some possible number of points. All right, so this is all we're doing. 28.95 divided by 36.77, okay, times 100, which is 78.77. 0.73%. Okay. All right, so let's talk about this a little bit. You know, one of the things I'm trying to teach you guys is about, thinking about whether or not your answer is reasonable and using information that you know to help you on test questions and honestly just in life in general when you're solving problems with numbers. So 100% equals all of it, right? All the things, 100%. It means I have everything that I could have. I have 100% of that thing. So, in a percent yield calculation, even though in our laboratory experiment and in the classroom lab, we yielded more than 100%, it is not actually possible to really yield more than 100%. So, if you are really not sure which one goes on top or bottom, remember that your smaller number probably goes on top. Not always. It's not going to help you in every circumstance, but more times than not, your smaller number of the two will go on top because your percent yield is going to be lower unless there is a massive amount of error in your experiment or your technique or something along those lines, which is what we experience because we're new scientists. Okay, you guys are just starting your techniques. There's all kinds of things that you would probably control for in our experiment that we just did if you did it again. And that's what happens in the real lab and in the real world. We refine things, we take information, we look at our error, and being able to give an actual number, like a percentage to our error, is awesome. So this is our answer. Okay, so just keep in mind, like whatever's smaller, probably want to put on top, because and again, that's not going to help you every single time, but it's a good rule of thumb. For example, like if your numbers are flip-flopped, then you should be thinking, is this reasonable? Let me go redo this. And if it turns out that you did have over 100% yield, great. But it should be a clue that you need to at least go back and look at it if the number you have on top is higher. Okay, really think about, is this right? All right, next and final question. A student obtains. Again, a student obtains, okay? That's not theoretical. You're not like a scientist from hundreds of years ago, calculating the molar mass of a chemical and writing a paper about it, defending it, and then going and contributing to the body of science. Okay, you're a student in the lab or a chemist that's in his lab, and this is what you measured with your experiment. So that is your actual. Okay, that goes on top. Actual 27.5 grams. Okay, and so it says the student should have obtained. Again, yes, it says the student, but it also says the should have obtained. We talk about that should have. So when it's something that should have, well, there has to be some standard to say like what we should have. And that is our theoretical, that's our theoretical value. It's our numbers on the periodic table that we use to calculate what we should have gotten through stoichiometry. Okay, so 31.8 grams is going on the bottom. So again, that is actual over theoretical. Okay, times 100. And when I put that in the old calculator, let's see, I get 27.5 divided by 31.8, okay, times 100. 86 point, let's just round it, 86.5%. 86.5%. Okay, perfect. So this is our theoretical, or I'm sorry, this is our percent yield, right? That equals percent yield. I want to, before we finish this up, just caution you. Do you think it would be really easy for a student to put the wrong number on top and then the other number on the bottom? It is. Okay. So when you're in a multiple choice test and you have a percent yield that's over 100, again, that's another thing. You just need to stop and say, whoa, 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 did I do this right? Okay. You might have, but just remember, like it's not the norm, it's the exception to have that happen. Because usually that means that there's something really wrong in that experiment that went on. And it's not really a real number anyway, if it's over 100%. So think like, okay, did I get that number? So even if it is in your multiple choice answer options, you should be cautious and redo it. Okay. All right. That is it. Thank you guys. If you hung with me this long, good luck tomorrow. I will see you soon.